Hello everyone. So in this lecture I am going to discuss the second method using which we can pipeline the higher order IIR filters, and that method is scattered look ahead pipelining. Okay, so it is used for pipelining higher order IIR filters, and suppose we have a transfer function like hz given by nz divided by dz, and let's say it is a nth order filter. Okay, so the idea is to transform the denominator. Okay, so denominator is transformed in such a way that it contains n terms like z raised to power minus m, z raised to power minus 2m up to z raised to power minus nm. Okay, so denominator is transformed in a way such that it contains n terms z raised to power minus m, z raised to power minus 2m up to z raised to power minus nm, where n is the order of the filter. It means that yn is computed using n past scattered states. So yn is computed using n past scattered states that are yn minus m, yn minus 2m up to yn small n minus capital N multiplied by m. So these are the m states using which we will calculate yn. So what we are doing? Okay, so for each pole in the original filter, we are introducing m minus 1 cancelling poles and zeros. Okay, so for each pole in original filter, m minus 1 cancelling poles and zeros, cancelling poles and zeros are introduced with equal angular spacing. Okay, for example, suppose the pole is at z is equal to p. So m minus 1 poles and zeros, m minus 1 poles and zeros for this pole. So for each pole we are introducing m minus 1 poles and zeros. For this pole we will introduce m minus 1 poles and zeros that will be at z equal to p e raised to power j 2 pi k by m for k equal to 1, 2 up to m minus 1. So the distance is fixed, the angle is changing, and by changing k like this, the angular spacings are fixed. Okay, so now considering the filter, nth order filter, IIR filter given by hz, that is equal to nz and dz, and dz can be written like this: I equal to 1 to n, okay, 1 minus p of I, z of minus 1. So n different factors we are factorizing dz into n number of different factors given by this expression 1 minus pi z minus 1. So multiplication of n number of such terms. Okay, so by scattered look ahead pipelining, okay, stage m stage pipelining. Let's say we are pipelining it by m stage pipelined. The transfer function will be given by hz, that is nz by dz. So nz as it is. So for each pole, so for I equal to 1 to n, the denominator, you can see that it is having n number of poles. So for each pole we will introduce m minus 1 zeros, cancelling poles and zeros. Okay, so k equal to 1 to m minus 1. So for I equal to 1, k equal to 1 to m minus 1. For I equal to 2, k equal to 1 to m minus 1, like this. So for each pole we are introducing m minus 1 poles and zeros. So that will be given by 1 minus p of I e raised to power j 2 pi k by capital M z minus 1. Okay, and the same number of poles will be added to denominator. So pi equal to 1 to n, shorthand notation for multiplication. And now k will start from 0 because it is already having 1 minus pi z inverse. Okay, so that's why we'll start k equal to 0, because we have to also include the poles which is already present. So now 1 minus p of I e raised to power j 2 pi k by m z of minus 1, and we can write this as equal to n prime z d prime z, new numerator and denominator. This is how you can perform a scattered look ahead pipelining. Okay, and also this value pi is less than 1 because this filter would have been a stable filter. So talking about the stability, so this is the real z, imaginary z, and p would have been inside the unit circle, and we are introducing extra m minus 1 poles and zeros with same radius, different angular spacing. Okay, so like this in this radius. So this filter is stable, unlike in a clustered look ahead pipelining where stability was not guaranteed. So here stability is guaranteed. Okay, so as pi would have been less than 1, stability is guaranteed. Okay, so now I am going to take an example, and using this method we'll derive the scattered look ahead. So now I am going to take an example, and using this method, scattered look ahead pipelining, we will pipeline this. So example, consider a second order filter given by transfer function 1 minus a1z minus 1 minus a2z minus 2. So this is a second order IIR filter. Okay, and let this can be written in this way: 1 minus p1 z inverse 1 minus p2 z inverse. Okay, in this form. So p1 plus p2 will be equal to a1. If you multiply this and compare these two terms, p1 plus p2 will be equal to a1, and p1 dot p2 will be equal to minus a2. So now I will be using this form instead of this. Okay, so this filter is having two poles given by p1 and p2, where p1 plus p2 is a and p1 dot p2 is minus a2. That can be calculated easily, solving some quadratic equations. Now HZ is three-staged pipeline. So pipelining it by three stage pipelining. So the value of capital M is 3, and this is a second order filter, so value of capital N will be 2. So HZ will be given by, so total number of poles in the system are 2, so for I equal to 1 to 2, and for each pole we will introduce m minus 1, that is m minus 1 is 2 cancelling poles and zeros, so k equal to 1 to 2, 1 minus p of I e raised to power j 2 pi k by m z minus 1, and in denominator I equal to 1 to 2, k will be start from 0 to 2, okay, because we have to include this factor also. So 1 minus pi e raised to power 2 pi k by m z minus 1. Okay, so now substituting k and multiplying, we have HZ, that is equal to I equal to 1 to 2, in numerator putting k equal to 1, so 1 minus pi e raised to power j 2 pi by 3, so putting k equal to 1, z minus 1, and putting k equal to 2, so 1 minus p of I e raised to power j 4 pi by 3 z minus 1. Similarly in denominator I equal to 1 to 2, putting k equal to 0, so 1 minus pi z inverse, okay, and this term as it is, k equal to 0, k equal to 1 this term, and for k equal to 2 this term, so 1 minus pi e raised to power j 2 pi by 3 z minus 1, this is for k equal to 1, this term for k equal to 2, so 1 minus pi e raised to power j 4 pi by 3 z minus 1. Now expanding it with respect to I, so this will become 1 minus p1, putting I equal to 1, e raised to power j 2 pi by 3 z minus 1, 1 minus p1 e raised to power j 4 pi by 3 z inverse. Now putting I equal to 2, so 1 minus p2 e raised to power j 2 pi by 3 z inverse, 1 minus p2 e raised to power j 4 pi by 3 z inverse. In denominator, 1 minus p1 z inverse, 1 minus p2 z inverse, and this term as it is, 1 minus p1 e raised to power j 2 pi by 3 z minus 1. Okay, so if you solve this, expand this and use this relation, you will have result as 1 plus a1 z minus 1 plus a1 square plus a2 z minus 2 minus a1 a2 z minus 3 plus e2 square z minus 4. In denominator, 1 minus e1 cube plus 3 e1 e2 z minus 3 and minus e2 cube z minus 6. Okay, so this is the 3-stage pipeline.